Welcome back. So today let's talk about a few potential applications of surface integrals. Now there are more applications of surface integrals than we're going to be discussing in this video. So we're going to focus in particular on how to use surface integrals to calculate surface area, mass, and center of mass. And then we're going to talk about how to use surface integrals of vector fields, which are called flux calculations, to calculate heat flow through a surface. Let's go ahead and get started. So the first formula that we have that we'll make use of in an exercise. If we have a surface denoted by the letter S, then the area of that surface can be found simply by calculating the surface integral over the surface S of the constant function 1. So if you want the surface area, just integrate 1 over the surface. So let's try with the following example, and let's let S be the surface formed by graphing the cone g of xy equals root x squared plus y squared on the disk x squared plus y squared less than or equal to 3. Alright, let's find the surface area. So our goal is to integrate over the surface S1, this surface area. So as usual, the first thing that we need to do is find a parametrization for the surface. Now this surface is the graph of a function of two variables, which means that we can use the standard parametrization where the x-coordinate is represented by u, the y-coordinate is represented by v, and the z-coordinate is represented by the output of the function at u equals x and v equals y. So next, let's go ahead and let's find the partial derivative of the parametrization with respect to u. If I take the partial derivative of the x component with respect to u, the result is 1. The partial derivative of the y component is 0. And applying the chain rule to find the partial derivative of the z component, I get 2u over 2 square root u squared plus v squared, but those 2's cancel each other out, and I'm left with this fraction. So similarly, for the v derivative, the partial derivative with respect to v, we get 0 for x, 1 for y, and v over root u squared plus v squared. Now when we're calculating surface integrals, our next step is always to take the cross product of these two partial derivative vectors. So let's calculate ru cross rv, I, j, k. Of the first function here, the first vector, 1, 0, u over u squared plus v squared, and then 0, 1, v over square root u squared plus v squared. And if we calculate the determinant of that matrix, then let's go ahead and we get in the I component, looks like we get negative u over root u squared plus v squared. In the j component, it looks like we get negative v over square root u squared plus v squared. And in the k component, it looks like we just get 1 from the k component. Alright, the next thing that we need to do is we need to calculate the magnitude of this cross product. If we were integrating a vector field, we do not need to find the magnitude, but since we're integrating the function 1, which is a scalar and not a vector, remember that we need to find the magnitude of this cross product. So squaring the first component gives us u squared over u squared plus v squared. Squaring the second component gives us v squared over u squared plus v squared. And squaring 1 gives us 1. Now notice that these two fractions here in the lead, when we add them together, the result of that is u squared plus v squared divided by the same thing, u squared plus v squared. So this is the square root of 1 plus 1. And so we get for the magnitude of our cross product the square root of 2. And therefore, our goal is to find the double integral over the region R of square root 2, where R, or if you prefer D, represents the set of all u's and v's which are valid for this region. So D here, or R if you prefer, is the set of all u squareds, v squareds, less or equal to 9. I'm going to go ahead and use the letter D. I think that's what we have used up to this point. But there's a little trick that I'm going to use to make it a little faster to calculate this integral. I'm going to pull that constant multiple of root 2 to the outside. And then I'm going to remind myself that if I integrate 1, double integral of 1 over the region D with respect to area is just equal to the area of the region D. Now D we called the disk of radius 3. U squared plus v squared less than or equal to 9 represented the disk of radius 3. Which means that its area is going to be equal to radius squared times pi. And so as a result, we get for the surface area of the cone square root 2 times the area of the disk, 9 pi. Okay, so this is how we can find the surface area of surfaces. We come up with a parameterization of the surface and use that to calculate the surface integral of 1 over the surface. All right. Let me give you another example of a potential application of surface integrals. So let's consider this formula. It says if we have a function u of x, y, and z, which tells you the temperature at a point x, y, z in some body of perhaps water or a solid body, let k be a constant which is called the conductivity. If I want to measure the flow of heat across a surface S in the body, so to perhaps measure how fast or how much heat is leaving the body, then you can do that in the following way. Take the double integral over the surface S of the gradient of the temperature function, and then multiply the result by the negative of the conductivity. So let's consider the following example. We've got some substance with conductivity K equals 6.5, and we know that the temperature at any given point in the substance is given by the function u equals xyz, u of xyz equals 2y squared plus 2z squared. So let's find the rate of heat flow outward across the cylindrical surface, y squared plus z squared equals 4, 0 less than or equal to x less than or equal to 4. So the first thing that I'm going to do is I'm going to sketch a graph of this surface. So let's just get a read on our surface here. We have a surface where the z and y coordinates are forming a circle of radius 2. So let me sketch in a circle of radius 2 on the yz axes. And then this circle is being drawn for x values from 0 to 4. So I'm going to extend this circle forward 4 units in the positive x direction. Okay, so the surface that we're dealing with has the shape of a cylinder surrounding the x-axis with a radius of 2 in the z and y directions. Now, because this surface has a circular nature to it, the standard parameterization is once again going to involve sine and cosine. So, for example, we could let y equal the radius cosine u, and we can let y equal the radius times sine of u. And then we can check that with these parameterizations, y squared plus z squared would be 4 cos squared u plus 4 sine squared u, which would be 4. So that satisfies the first condition. Now, x is behaving in a way that's fundamentally independent of either y or z. Y and z had an equation which related those two quantities to each other, but x doesn't have any equation which relates that guy to either y or z. So we will define x in terms of just the other parameter. We will define x equals v. Okay, so now that we have set up some parametric equations for this cylinder, let's think about the values of u and v that would be allowed. Now, y and z are creating this circular motion around the outer rim of the cylinder. And u is representing an angle, since it's being put into cosine and sine. So that u value, in order to go all the way around the circular rim, would have to go from 0 to 2 pi. Now, x is being represented by the parameter v, and x was said to be able to go between 0 and 4. And so v will also be allowed to go between 0 and 4. So this would be the description of the region we have usually called D, where u and v are allowed to roam, where those values are located. All right. Now that we have established a parameterization for the surface, the next thing that we're going to need to do, as usual, is find r sub u and r sub v and their cross product. So r sub u, if I take the derivative with respect to u of x equals v, the result is 0. If I take the derivative with respect to u of 2 cosine u, I get negative 2 sine u. And then if I take the derivative with respect to u of 2 sine u, I get 2 cosine u. If I repeat the same process, but I take the derivative in the v direction, then the derivative with respect to v of v is 1. But the other two coordinate functions don't depend on v at all, so these two derivatives would just return 0. Now let's take the cross product. Okay, so let's fill up our matrix with the traditional I, j, and k, and with our coordinates u derivatives, and with our coordinates v derivatives. And let's calculate the determinant. And we have negative 2 sine u times 0 minus 2 sine u times 0, result 0. In the j component, we have 0 times 0 minus 1 times 2 cos u. Make it negative, we get positive 2 cos u. And in the k component, we have 0 minus negative 2 sine u, so positive 2 sine u. Now this is the moment where we look back up at the original problem and we remind ourselves that the gradient of u is a vector, and this dot product is another hint to indicate that this is the surface integral of a vector field. This is flux that we're calculating right now, which means that we do not have to find the magnitude of this cross product. The magnitude of the cross product is only necessary when we are taking the surface integral of a function, not of a vector field. So let's leave this here for right now. Our next job is to calculate the vector field gradient of u, where u was given by the function 2y squared plus 2z squared. U does not have any x component, so that partial derivative is 0. The derivative in the y direction is 4y, and in the z direction is 4z. And so, if we take the parameterization, where we had x being replaced by v, y being replaced by 2 cosine u, and z being replaced by 2 sine u, and plug that in, we now have 0, 8 cosine u, 8 sine u for our vector field in the correct parameters. Alright, so now let's take the double integral over the region D of the gradient of u dot product Ru cross Rv as a double integral. Now if I look at that dot product, here is the gradient of u, and here is the cross product that we calculated earlier. And so the dot product gradient of u dot the cross product of the partial derivatives is going to be equal to 16 cos squared plus 16 sine squared, which is the constant value of 16. And therefore, what we are really integrating over the region D is just the constant number 16, which, as before, we can pull outside of the double integral, leaving us just the double integral of 1 over the region D. But we're going to use the same time-saving technique as last time, and we're going to remind ourselves that this integral of 1 with respect to area is equal to the area of the region D, where u and v occupy. And the region occupied by u and v is just given by this rectangle, where v goes from 0 to 4, and u goes from 0 to 2 pi. So to find the then area of this rectangle, we can just multiply length times width, 4 times 2 pi. And we get 16 times 8 pi, which is some number. I think it's, 128? 128 pi. So finally, what is the rate of heat flow? The rate is equal to negative k times the surface integral of the gradient. We found that the surface integral of the gradient was 128 pi. We were told that the conductivity was 6.5, and so this product of 6.5 times 128 pi, make it negative, would be the rate of heat flow outward across this cylindrical surface, not including the circular caps at the ends of the cylinder, just including that cylindrical tube on the outside.